Thank you, Bill, for inviting us to the AI Camp. It's a pleasure to be here. Um, so for today's webinar, we're going to deep dive into the understanding what is the model ops first, and then what are the challenges we face in the production when it comes to the model ops. So for today's topic, we'll just go through the model ops and how to deploy the ML models in the repeatable and the scalable process. So it's provide efficiency and the ROI for our enterprise customers. We'll be doing the technical deep dive in our monitoring model performance led by our VP of Data Scientist, Nina Zumel. All right, before we deep dive, I just want to do a quick recap of our previous webinar led by our head of product, Yunus Amar, about what is Valeru. Valeru is a compute engine platform which focuses heavily on the last mile of machine learning journey. We are a fast computing engine. We focus on the last mile into production, and we help enterprises to put their models into production quickly and scale them in an efficient manner. Okay. So this is a picture which actually describes the best when it comes to model ops, why we need model ops. So before we look into what is model ops, I want you all to think of a scenario which is a very general scenario for every enterprise, right? There's a business stakeholders, there are the subject domain experts who are trying to, solve a business challenge, right? And there's a data scientist team on the other side who are very well efficient with the help of data. They can solve that problem. But when it comes to managing those two together, the R&D, the data scientist team, and the business stakeholders together, that's where the model ops comes into the picture. It's a heavy duty operation, building the model taking the model all the way from the R&D to the production in a way so that it can provide a good ROI to the enterprise. It's focused on the providing the ROI to the enterprise. And there are certain gaps when the model transition from one phase to the other phase. So that is model ops. When it comes to handling and managing the models from one phase to the another phase, in the previous diagram, we showed you the model building phase, which is mostly handled and heavily driven by the data scientists. They have tons of data. They can build their amazing models using any training resources that they have at their disposal. But now, what is after that? When the model transition from the training phase to the deployment phase into the production, there are certain transition challenges that they face. Similarly, in the model deployment phase, most of the roles and responsibilities are handled by the ML engineer or the DevOps engineer, which they look at the infrastructure. How much infrastructure we have? Is the infrastructure compute going out of the budget? So they look at those responsibilities. Then the third phase comes in when the model actually goes from the production to actually providing the ROI to the enterprise. That's the model selection phase. Let's assume a scenario where there are thousands of models in the production, right? But in order to understand how all those 1,000 models are working, right, and which model is performing well, and making an informed decision about, okay, now this model is not performing well, it's degrading in its performance, and it's trying to retrain the model and send it back to the data science. So this completes the whole model ops cycle from end to end. As we discussed, Valeru focused on the last mile delivery, and we specifically help data scientists as our user, helping them to transition their amazing R&D models into the production and going through the whole cycle of the deployment and the selection phase all the way back to them when it's time to retrain. So some of the challenges we have highlighted here from when it comes from training to putting into the production is converting and preparing the training model for the production environment. And also, if you have thousands of models, how will you scale the models effectively from training to the production so that they're manageable in the production environment? Similarly, once the model is in production, somebody has to take care or look at the models, whether it's performing well, right? Or if you have multiple models, compare the model side by side, which is performing well, which is not performing well, and take it back. So ability to have that experimentation framework in the backend help enterprises to understand, is that model even worth putting into the production? Once we identify those challenges, so those experimentations we can do either by the A/B testing, canary test, or the shadow deployment. We'll deep dive into this in a later series. But once we identify the best performing models, we go into the selection phase. Selection phase is actually where you actually look at the model individually and track the performance against the data that they're inferencing. So like the data trait, whether the model is accurate enough or it's degrading in their performance. And based on looking at the model, you subject domain experts make an informed decision. Okay, now this model is not working well, and it's time to go back to the training environment and retrain the model. So at all three the different levels, you'll see there is a heavy part where we need a inclusion of data scientist. Data scientist has to know how it is performing in the production, how is it performing at the model selection phase, and they have to collaborate with ML engineer and the subject domain experts all together in all three phases of ModelOps. So how they will collaborate effectively, that's the one challenge, and how we transition the model from one phase to another seamlessly so that there's a very less manual time when it comes to completing the ModelOps cycle. So these two challenges we try to tackle in our platform in the Valero. So how Valero does it? For the transition from the training to the deployment phase, in Valero, we do it with a simple step. All you have to do is define your define your production compute usage for that particular model that you want to put in production. And then all you have to do is just upload your training model. For this, for the sake of example, we are using the Onyx model, but literally you user can upload their own training model the way that as it is. What the Valero will do, it'll take the model in the backend and it will convert into the Valero model object, which runs and gets deployed quickly in a one single command. It literally takes 45 seconds. So if you look at this example, model, upload model and deploy, we are taking the model and deploying it with a pipeline named fraud. And once you deploy it, the pipeline is active in the production environment, and you can actually go and run the inference request against the pipeline. Now, if you focus on the second part, when it's into the in the active deployment, and what after that, right? So once you have, let's say a scenario where you actually running a deployment, active deployment, and the data scientists say, oh, there's a new version of that model. But before taking out the previous model and putting the new one, everybody want to verify whether the new model was as expected, the first model in production, right? So in ideal behavior, what somebody will do, they'll take off the model from the production, they'll compare the results and put whichever the model is working best, they put it back. But how Valero is tackling that differently is we provide the deployment URL. This is our engine endpoint, which is active and which is a single endpoint. And beneath this single endpoint, you can connect your different experimentation frameworks like the A/B deployment or the shadow deployment or the canary deployment. So you can have two models connected directly with the same endpoint as a base model and a challenger model, and identify which experiment you want to run out of these three. It will help. How it will help? It will help enterprise from the there is no downtime. You're not taking the model active model out. The pipeline is always active, so there is literally no downtime. You can do all your experimentation in the backend without knowing from the outside world, right? You guys are experimenting in the backend. So that's how you can do the experimentation in the backend. We'll be showing you the demo shortly after this slide. I'm going to deep dive into the model management side of the demo for now, and then later my colleague will deep dive into the model monitoring and the observability demo. Okay. All right, so this is our platform. I hope everybody can see it. So this is the Wallaroo dashboard where all the team members across the business stakeholders, subject domain experts, the data scientists, the ML engineer can work together on a single model or a single pipeline. As for example, we can run different experiments here. As you can see, we have listed 4 different experiments. And for today's purpose, I'm going to create a new experiment for us. Let's call it AI camp. Let's call it AI camp, let's say. So we create the AI camp, and I'll go to my AI camp workspace. I'm the only person here, and I would like to invite my data scientist friend here to help me understand how my model is working. So I'm going to invite Nina to this. Later, she'll use this workspace. I don't have any model. I don't have any pipeline in this yet, right? For the sake of this demo, I'm going to go back to my another workspace and show you guys the pipelines. So these are the pipelines that we have tested in like last 7 days. I can go and look at these pipelines, right? Similarly, I can look at the models that we have used in the past. So whenever I click on a particular model, it will give me a detailed tags about when the model was used and in which pipeline it's being used currently. And if I have any questions around that model or anything, I can go and simply ask. Hello, let's say hello. So this will be broadcasted to all the members that are there in my collaboration workspace. So let's go back to our model workspace that we just created. And I invited my friend. Actually, I'm going to open the. So once you click on the launch Jupyter Hub, it will open a Jupyter Hub within the Wallaroo. And here we can actually go and run our demo. So for simplicity, we're just going to run the Wallaroo client and switch the workspace and deploy a simple pipeline for the testing purposes. So it's pretty simple. We import the Wallaroo package. We authenticate the client. That's only the authenticated authorized users can use this. It's successful, and I can list all the workspaces that's in there. Invites, and we can see all this workspaces, and the last one is the AI camp. So I'm going to go to the 8th one. Oops. Yeah. So as you can see, my current workspace is AI camp now. And what I'm going to do here is I'm going to upload a model and deploy the pipeline, the active pipeline in the same workspace. And it's taking 25 seconds. So let's wait for 45 seconds. And it's done. As a result, I can see all the pipelines which are in Wallaroo. So these are all currently not running, and this is true. This is the active pipeline that we just deployed. Now, if I go back here, I can see my active pipeline. I can see this pipeline is running actively. If I click on that, I can see when it was deployed, which model it is using, and what is the configuration. I go back here. I'm going to make sure this is the pipeline that I was using. And I'm going to use the deployment URL. So this is, oops. Okay, I guess. All right. I'll leave it to the next, in the next demo. We can see why. Oh, I know. It's, never mind about that. Sorry about that. Okay, so let's verify the active pipeline. It's running and it can infer from a single record from the file. So let's run this. Now we can see, yes, it's active and it's running, and I can do a single record, which is running just fine. It's all right. So if I go back, I can see the pipeline steps. I can see the models in here, and when it's running the active data, I can see the data here as well. So let's go here and run a sample data against the pipeline. I'm just gonna verify one more time, and I'm gonna load the data. It's a reference data. This is the pipeline that we want to run for, and this is our sample data which is running. And if I go back to the metrics, it will start showing up here. So now you can see the data is coming. So going back to the model management piece, as a ML engineer or an infrastructure ops engineer, I would like to see this information. How many requests per second? What is the cluster inference rate? Is there any inference latency? Which will help me understanding the pipeline health overall, how my infrastructure is behaving, right? And similarly, when it comes to monitoring the model, data scientists also want to see how the model is performing against the demand that is generating from here. They want to deep dive into the certain aspects of the model feature so that they can train the better model next time. So that's where it comes to the analytics part. And over to Nina. I'll invite Nina for giving a deep dive introduction about the analytics part and the model monitoring stuff. Nina, over to you.
Okay, great. Thanks, Dipika. So let me share my screen now. Okay. All right. Just kind of to reiterate what Dipika said, the theme of this talk is that the data scientist's job doesn't end once the model is deployed. It's actually equally important for data scientists and, in fact, their other business stakeholders to continue to have visibility into models when they're in production, to see how they perform and behave so that they can continue to learn, observe, monitor, and even to improve the model-driven, data science-driven processes, decision processes that are active in the business. So what we're going to do for the rest of the talk is we're going to do a little bit more of a deep dive onto three aspects of model observability in production that we believe data scientists and other business stakeholders should be involved in, and why it's important to have them in production. So basically, we're going to cover some basic domain-specific data validation on the inputs that go into the models, some simple anomaly detection on the predictions, that come out of the models. We're going to talk about detecting data drift and why that's important, why we need to do that. And we're going to touch a little bit on model explainability and why that's actually important to have in production as well as in training. So let's start with some basic data and prediction validation. What I mean by this is the ability to specify and to continue to monitor domain-specific information about what constitutes, quote unquote, reasonable inputs and into a model and reasonable predictions that come out of the model. Because this kind of information is generally domain-specific or even problem-specific, the most important people, the most appropriate people to be to know this are, in fact, the data scientists and other subject matter experts. That often makes them the most appropriate people to try to specify the appropriate validation checks in production, and occasionally makes them also the most appropriate people to monitor, for anomalies and strange behavior validation violations also in production. And these things are generally easier to talk about with a concrete example, so let's use one. Imagine that we're a real estate concern, and our data science team has developed models to predict home sale prices in a particular housing market. Now, as a data scientist or the subject matter expert that worked on this model, we may happen to know that for some particular housing market, the houses in this market generally tend to sell in the range of, say, $200,000 to $2 million. Now, it's not impossible for a house to sell for outside of that range. Neither is it impossible for a model to predict a value outside of this range. And the model might not even be wrong if it predicts a price outside of this range. But it may be a sufficiently unusual event in this particular housing market that for policy reasons, we, the company, might decide that when the model makes predictions that are outside of this usual typical range, that we would like to have those predictions double checked or sanity checked by an actual real estate agent, just to make sure that the model hasn't gotten to some weird corner case. And furthermore, if the model begins to start predicting atypical prices at an unusually high rate, a high frequency, then we might like to actually alert a responsible person that, hey, the model is doing a lot of weird out of range predictions. So, we would like to go check on what the model's health, on the system's health, maybe intervene when that's necessary. And that's kind of, we can take a little break from the slides now and kind of see how that works in Wallaroo. Actually here, I am going to interact with the platform. Dipika showed you interacting with the platform through the dashboard. I'm going to do it through the notebook. So let's load up some appropriate libraries. We're going to connect to the client and we're going to attach to the workspace that Dipika just created for the two of us. And I'm going to upload our house price model into this workspace. Now, what I'm going to do is I'm going to create a deployment pipeline for this model, and I'm going to add the validation checks that I just talked about, the ones on the house prices. So what I'm going to do is I'm going to set, these are some expressions to express these validation constraints. We'd like to add a check that the model's output is greater than $200,000 and less than 2 million. We're also going to add an alert. So basically this expression is the opposite of that validation check. It says whenever the model's prediction is greater than $2 million, if this occurrence happens more than 100 times in a 24-hour window, we'd like to, that's unusual and we'd like to send an alert about it. So I'll define those expressions. I'm gonna build a pipeline. I'll add the model to it. I'll add our 2 validation checks. And I'll also add our alert condition. And what's going to happen is if this alert condition ever triggers, it's going to send an email to the responsible data scientist, which in this case is me. So it's going to send an email to my email address. So we can attach all of that to the pipeline and then deploy it. And that'll take about 45 seconds. And then what I'm going to do now that it's deployed is I'm just going to show you what happens, if we throw a typical house query at it. I think Dipika didn't go too much into the detail. This is sort of the internal representation of the inference results that come from the model pipeline. Generally speaking, what would happen in a normal situation is these inference results are sent by the pipeline onto the next step of whatever decision process this model is involved in. In this case, we're just sort of inspecting them through the notebook. And what you see here is this is the pipeline that ran. Here's the output for this particular house. It was predicted to sell for $1.5, $1.6 million. This is the model. And this is kind of the information of interest for us right now. This particular field monitors whether or not any of my validation checks have failed. And in this particular case, because this house is in a typical range, it has not failed. But we can try it with a house that I happen to know ahead of time is very low priced. So this house was predicted to sell for $187,000, and that violates our constraint that we would like the output to be greater than $200,000. And similarly, if I throw in a house that's extremely high priced, this will violate the other check. So we can try looking at several houses. We can query this pipeline with several houses, some of which are typical, some of which are unusual, out of range. And as I said, the inferences from this pipeline are now getting sent on to the next process, whatever the next process is in this decision process. But the pipeline also logs all of the inferences that it does. So we can actually look in the logs. I'm going to pull the logs. I'm going to put them in a slightly friendlier format. And what we can see here is that these are the inferences that I just made. Here are the house predictions. And you can see that the logs actually record whenever anomalies occur. And this is a list, which is a little hard to read right here, but in case multiple validation checks were violated, you could actually see them all. And like I said, this is a little hard to read, but you could actually look just at that column of that data frame. And you can see that sometimes the left-hand validation check was violated, and sometimes it was the right-hand side. And of course, if this were to happen, I'm not going to show you what happens if this happened. If we were to run this a lot and we were to get more than 100 validations of, I think, the right-hand validation check, then alert would be triggered, that would be logged, and an email would be sent to me to say, hey, the model is behaving sort of strangely, so you need to go look at it. So that's kind of an example of simple validation checks. I'm just going to undeploy this pipeline to release the resources. Whoops. And we'll kind of go on to the next step in our model observability journey, and that is detecting data drift or data distribution drift. And what this means is that we would like, the data scientists and also the other business stakeholders, would like to monitor the values of key inputs that go into the model, or the output that comes out of a model, to check if the distribution of the values of whatever field we're monitoring is changing. Specifically, what we want to check is whether or not that distribution is changing from what, quote unquote, the model expects, or in other words, what the model was trained on. And the reason we care is that if the environment that the model is operating in, in the real world, begins to change from what the model's expectations are, then the model can no longer perform as well as we would like it to. This is an issue that is known as concept drift in machine learning terms. And concept drift is generally an indication that it's time to retrain your model on fresher training data, so that the model can, so to speak, recalibrate its understanding of the environment that it's working in. Again, this is easier to talk about with a concrete example. So let's imagine this time that we've got a model to predict credit card fraud. So basically, this model takes as its input a representation of a credit card transaction, returns a probability that that transaction is fraudulent as a probability. So let's say that we trained and deployed this model in early 2019. And at that time, when we ran it, we eventually became to understand, how the predictions from that model were distributed. So basically, we have an understanding of how that model should be behaving. And let's call this the baseline distribution. And the baseline distribution possibly looks like, as an example, this green distribution that's on the top of both of these charts. This is the same distribution. And it reflects what the model sees about the world. Mostly, most credit card transactions are legitimate. So most credit card transactions are scored very low by the model. But there's this very low volume, tail, so to speak, of transactions that are increasingly more suspicious to the model. So they score higher and higher. And at some point, some of these score so high that presumably the business decision is to reject those transactions. Now, we want to continuously monitor these, the values that are coming out of the predictions that are coming out of the model, and check for drift. So let's say that we're checking in 1 month intervals. So as an example, let's take the month of April 2019. We're gonna, over the time interval of April 2019, we're gonna collect all of the predictions that the model made, and we're gonna look at the distribution of those predictions. And suppose it looked like this distribution that's on the lower left-hand side. And you can kind of see visually here that this is basically the same distribution. I mean, it's not exactly the same, but it's substantially the same. And so we could say, at least visually, that the model in April 2019 is behaving pretty much as we would expect it to behave, which probably means that the environment that the model is working in is also pretty much as the model expects. Now let's jump ahead a year, and we now look at, say, April 2020. And again, we do the same thing. We collect all the predictions that that this model made over the month of April 2020, and we look at the distribution, we compare it to the baseline. And this time, what we're seeing is that these distributions, in fact, visually do not look the same. There is an uptick here of transactions that the model believes are at least moderately suspicious. And now what does this actually mean? Well, one thing it could mean is that there was, in fact, an unusually high level of fraudulent activity in April 2020. That's always possible. Another thing it can mean is that there's been some change in consumer behavior since this model was trained, which causes transaction types or transaction behavior that used to be considered highly correlated with fraud to be less correlated. Sort of a simple example that might come to your top of my head, at least, is one of the classic signs of fraud used to be, or maybe still is, that you're buying very expensive goods, like expensive electronic equipment, on your credit card and having them sent to a billing address, to a shipping address that is different from the billing address. This is sort of one of the classic examples of a potentially fraudulent behavior. That might have been true in 2019, but when you get to 2020, we're living in a kind of different world at that point in time. More people are working at home, more people are taking classes online rather than in person. People are no longer able to visit family and friends in person anymore because of health concerns and the pandemic. So it might be the case that it's more important for people to kind of upgrade their electronics to deal with this new world. And it might also be the case that there's more activity where people are buying electronic equipment for other members of their family who need a little financial help with that. So I might, for example, have bought a new laptop or a new webcam for my parents because I'm no longer visiting them and I have to Zoom with them. Or I might be buying a new laptop for my son who's away at college and is now taking his classes online. So that constitutes an example of a change in consumer behavior that means that the model no longer understands the world as it was when it was trained. Now, just looking at this particular graph, we don't actually know which of these two cases this is, whether it's high fraud or actual concept drift. But the first step in being able to troubleshoot an issue is to know that the issue exists. And therefore, it's very important to sort of monitor for changes in the behavior of the model's outputs or even their inputs. So then we get to the question of, well, how do we actually do that? There are a lot of different ways to do it. Wallaroo has a particular approach that we have called, which is now implemented in our production platform, and we call it Wallaroo assays. They're monitoring assays that we attach deployment pipelines to monitor inputs or outputs looking for drift. And sort of the general procedure is, and let's keep with the example that we're using, monitoring the output of this fraud model. Once the model has been deployed and is running, you take an initial time interval to collect data about how that particular output is distributed. And we'll call that kind of the baseline distribution. It's the description of how we expect the model to behave. And then we take that baseline distribution and we define some sort of binning scheme over the predictions. There's different ways to define a binning scheme. The default one that we pick is to divide the bins into such a way that every bin contains the same fraction of predictions. So in this case, by default, we use 5 bins. So every bin holds 20% of these predictions. Once we've got the binning scheme and the baseline, we can go over to the next data interval. We're continuing to monitor and we're continuing to collect information about the output of this model. We collect that distribution, we collect those values, and then we bin them according to the baseline binning scheme. And then we ask ourselves a question, well, how different is the binning of this data from the baseline? If the answer is not different or not very different, then we say, okay, fine, it looks like things are pretty much as we expect. We do not detect any distribution drift, and we keep going. We repeat for the following time interval. We look at the predictions, we collect them, we bin them according to the baseline binning scheme, and then we ask the same question, how different? And if in fact this time the binning looks different, we say, okay, there seems to be some indication of drift. We will flag that so that the people who are involved in monitoring this model can know about it and intervene, potentially retrain the model. And basically this entire loop is just repeated for the life of the pipeline as it's running. So that's the basic procedure. It's pretty straightforward. It's easy for people to understand, which is one of the things that was important to us. We wanted a method that was reasonably intuitive for people to understand, both to set up and to understand the results of, without necessarily having to have a PhD in statistics or machine learning. Just accessible. So this is a fairly accessible process. The one question I haven't answered is, well, how do we actually answer this question? What is the definition of quote unquote different? Well, basically what we need to define the notion of different is we need a metric that can describe the difference between two distributions, or in this case, two binning schemes. Again, there are a lot of different metrics, and we actually implemented a few of them, but by default, the one that we choose first is what is known as the population stability index. I'm not going to get too much into the definition of what that is. For those of you who are familiar with the Kolpak-Liebler divergence criterion, this is sort of a symmetric version of that. If you don't know what that means, don't worry about it. The reason that we picked population stability index is that it comes with a nice kind of heuristic rule. Basically, if you take two distributions or two binning schemes and you measure the population stability index value between them, if that value is less than 0.1, you can take that as an indication that those distributions are not different. If the value is greater than 0.1, then the distributions, that's an indication that the distributions are different. And if it's greater than 0.2, that's a very strong indication that the distributions are different. So just to give you an idea what that actually looks like, we can go back to the distribution that was calling April 2019. And we can imagine binning that against this baseline binning scheme that I had defined, and calculating the population stability index between the two of them, which in this case comes out to about 0.076, which is much less than 0.1. So you can say quantitatively, these two distributions are probably not different. But if we jump ahead to the distribution I was calling April 2020, actually even visually, you can see that the binning, when you bin according to the baseline binning scheme, it comes out very differently. We're getting way more values in the upper bin than we should, which is consistent with what we saw visually. And if we calculate the population stability index, we get a very, very large number that's way above 0.1 and is definitely an indication that these two distributions are different. So those were all kind of notional examples. Those were not results that came out of the platform. So I'm going to show you some results of how this looks in the platform and how we detect data drift on running on our deployed pipelines. So I'm going to do this in the notebook again. We're going to load some libraries. We're going to connect to the clients. We're going to go to a different workspace. Actually, this is this is the same problem. This is the house price model problem, but this is a different workspace with a different model in a different pipeline that's been running for a while, so that I can show you how the assays work. So we're going to pick up the pipeline of interest, the model in the pipeline that's actually doing the predictions. And following the procedure that I just showed you, the first thing we need to do is define a baseline distribution that we're going to check. We're going to check the outputs of this model and look for drift in the outputs. So for the purposes, let's say that this model got deployed at the beginning of this year. And for the purposes of this demo, I'm going to pick as a date the baseline the first day of the year, which is we're going to go from midnight January 1st to midnight January 2nd, just for the purposes of this demo. So here I'm going to define the baseline period, which is what I just said. We're going to build what we call an assay that is associated with this model in this pipeline, and it has this baseline period. And once we've done that, we can look at some basic statistics on the baseline, basically mean, max, median, and we can also look at a histogram of it. And so this is a representation of our baseline distribution that we are going to be checking this model against. This particular housing model happens to have been trained on log price rather than absolute price, which is why the values look the way they do. We can also look at the binning scheme, which is not terribly exciting, visually speaking. It's basically 5 bins that have been defined to have 20% of the data in them. The interesting part here is basically the bin edge definition. So basically the first bin, 20% of the data from this distribution will fall in the range 11.9 to 12.6. Another 20% will fall in the range 12.6 to 12.8, and so on. And you can actually see that as a data frame as well, if that's better for you to work with. Now, once we have a baseline, we can start monitoring the output of this model. What I'm actually going to do is I'm going to do this first against historical data rather than setting it live. I'll set it live later, but first we're going to run it against historical data, which is a functionality we offer both so that people can sort of play with this and understand how all the settings work, and also so that people can make sure that the settings for this particular pipeline are appropriate before they just sort of fire it and let it go. So what we're going to do is we're going to run this assay against a month's worth of data from January 2nd to February 1st. And what we're going to do is we're going to take intervals of every day, every 24 hours, we're going to take an interval that is the past 24 hours, look at the distribution in that of predictions in that window and compare it to our baseline. And I'm going to do this. A lot of the settings of this are default settings for our assay, but I'm going to do it slowly and in steps so you can sort of understand what's going on. So we're going to set the last day of our historical analysis to midnight of January 2nd. I'll build the assay up fresh again with the same pipeline model and baseline period. I will explicitly set the assay to monitor the output. And I will explicitly set the observation period or interval to every 24 hours and the width of the window to also 24 hours. So again, every 24 hours, this assay will look at the predictions that were made by this model over the past 24 hours and compare that distribution to the baseline. We're going to set our threshold to 0.1 because that's a good place to start. We're going to tell this assay to run until midnight of February 2nd, or February 1st, whatever that is. And then we're going to, rather than having this logged into our production logs, we're actually just going to save those results into an interactive object so that we can look at it. And that's going to take a little bit of time to run. Once it does, we can look at the results. So what you're looking at here is the results of this assay, which ran every day from January 2nd to this is the end of January. And this y-axis is the difference score between that day, that window's distribution and the baseline distribution. The green dots are those days when the distributions were not different from the baseline. And then the red dots are when some difference occurred. So basically what happened is this particular model ran as pretty much expected until about the 14th of January, and then something happened. Things got very different, and then for whatever reason, things got back to normal again. So when we get this working in the dashboard, which we are, of course, going to do because it's a more pleasant way to interact with things like this, you would be able to drill down, you will be able to drill down onto these different dots to actually see what's happening on those particular windows of time. What I'm going to do is through the notebook, I'm going to drill down on this day, which is January 2nd, on January 14th, when things are just beginning to change, and January 15th, when things are noticeably beginning to change. So first, let's try January 2nd. And here is the result of the binning of the predictions from January 2nd. The blue bars represent the baseline binning, and the yellow bars represent binning the predictions from January 2nd into these same bins. And as you can see, it's about what we would expect. Every bin holds about 20% of the data, more or less. If we look at the population stability index score between the baseline and this window of distribution of predictions, we see that the score is 0.01, which is much less than our threshold. So we can say, yes, indeed, the distribution on January 2nd is pretty much what we expected as defined by the baseline. Now let's try looking at January 14. And what we begin to see here is that there is some sort of upward creep in the distribution of predictions. So basically, we're getting more predictions than we might expect in the range 13.0 to 13.3, and fewer than we might expect in the range 11.9 to 12.6. And if we take the score between this window distribution and the baseline distribution, we see that the score is just over 0.1. So we are just beginning to see some indications of some kind of drift in the behavior of this model. And then we go to the next day. Right, now something really dramatic has happened. There's way more predictions than we would expect in the upper range. And in fact, some of the predictions are so high that they're actually falling into what would have been considered an outlier in the baseline distribution. And there's basically nothing's getting predicted down in the lower range. And if we looked at the population stability index score, we see that it's very large. It's 3. That's much, much larger than our threshold. So we know that something is going on. Now, what is going on? We don't know yet. And I will get a little bit more into that in a moment. But before I get into that, remember, we were running this on historical data. And what we actually would like to do is take this kind of assay and run it on the running pipeline and just having it continuously monitor. So let's just say that we had gone through this exercise. We decided all the settings were correct. And we were like, OK, we want to go live now. So we would basically do the same thing. We're going to define the same assay with the same threshold. At this time, instead of, I'm not going to show this, I'm just going to show the code. Instead of, running it interactively, we're actually going to upload it into the system. This command will attach this assay to this pipeline. And now every day, every 24 hours, it will look at the previous 24 hours of predictions and compare the distributions, looking for indications of drift. And after a while, we can get the assay results for further analysis the same way and interact with them the same way that I just showed you. Okay. All right, so now we know that we can detect some sort of distribution drift in either inputs or outputs, in this case, in the output of this particular model. But we don't know, even though we know that a drift has happened, we know something has happened, we don't know exactly what. And that is kind of the next step in the model observability journey. It would be really nice to take that window of time, all of the predictions that were made, say, on January 15th, and say, okay, why is this happening? What is causing, what changed in the world to cause these predictions that seem so unusually distributed? That is kind of the next step that we'd like to have implemented in Wallaroo. This is a work in progress. It's not been released into the product yet. We're still in that process. But what we are working on currently is trying to have some sort of model explainability, specifically for those of you who are familiar with it, SHAP analysis style explainability integrated into our platform, so that on production data, you can actually do an analysis of the relationship between feature values and predictions, and try to understand, for example, why is it that these predictions look sort of so out of whack. I'm not going to get into the details of what SHAP analysis actually is, other than to say it's a model agnostic way of trying to attribute the influence of various features on a specific particular prediction, and then kind of taking those insights and kind of dealing with them holistically. Again, it's easier to talk about it with a specific example. So let's say we have a specific house. We have a specific house, and this particular house, these are the features that we look at of the house, and there are specific values for this house, which we're not showing. And this particular house was predicted to cost, to sell for $565,000. What SHAP analysis and other model explainability type functionality can give us is the ability to say, well, what is contributing to that prediction? And in this case, what we see is that the most important feature here is the size of the house. Basically the square foot living area of this house. The square foot living area of this particular house contributed $70,000 to the price of the house. And conversely, the location of this house, as expressed through the latitude and the longitude, together had sort of a negative impact on the price of this house. Basically, the latitude and longitude of this house together sort of detracted from these predicted price by 31 plus 7 is about $38,000. So basically what we're saying is this is a nice large house, and that's a good feature, but it's also in a slightly less desirable neighborhood. And that's a feature that brings the price down. We can do other kinds of things with SHAP analysis. We can take a particular feature and see and try to understand how that value, the value of that feature affects house prices over the entire sample of predictions that we're looking at. So if we look at latitude, which is the north-south position of the house, we can see, I happen to know that for this particular housing market, the city center is right about here. So what we're seeing here is that as north-south-wise, as the house comes closer to the city center, it becomes more expensive. And as it gets further from the city center, it gets less expensive. And in fact, what we can also see is that as the house gets further from the city center to the south, that has an even more negative impact on the price than moving away to the north. As I said, this is not yet implemented in the Wallaroo platform. For those of you who are familiar with SHAP analysis, you probably know it's a very compute intensive algorithm. So there are some issues with trying to incorporate this into a production platform. We don't want to, basically read out all the resources of the platform, just on these analyses. So we are working on ways to address those issues. And we hope to have an early version of model explainability incorporated into the platform very soon. And we will be happy to show it to you when it happens. So that's about it for the things that I would like to talk about in this talk. If you are interested and you want to know more, please do check out our website, www.wallaroo.ai. You can check out our blog. You can look at the documentation for our platform. If you want to get in touch with us, please get in touch at community@wallaroo.ai. And if you're curious enough and you actually want to play with a version of our platform, we just yesterday, I believe, released our community edition for general release. That's a free version of our platform that allows you to sort of experiment with the different features that we offer for deploying and monitoring models in production. You can go to portal.wallaroo.community, sign up to get a license to download this. And that is it. Thank you very much.
Great. Thanks, Nina and Dipika, for the presentation and share the a great product and tools for the machine learning operations. I see a few questions in the chat. Maybe you can go through them. Just a quick reminder, if you have questions, now it's time we have a few minutes to do the Q&A. And if you prefer to speak or ask questions, you can just raise your hand. I will unmute you to speak or ask questions.
Okay, I am looking at the questions quickly. I see that someone asked, Narendran asked, whether we can attach assays to model inputs, and the answer is yes.
Yeah.
Yes, it can. High-level overview of the workflow architecture. I believe that might be in our documentation, Dipika?
Yes, it's there in the slide 5, which we'll share after the webinar.
Yes. And thank you for the person who forwarded the article about SHAP. As I didn't really have time to get into the technical details of it. It is a very interesting procedure, and I would recommend that to you all. And those are the questions that are in the chat right now. Is there anybody else? Ah, here we go.
There's one more.
Focused on the last mile, is it focus? Yes, okay, so yes, we are concentrating on the deployment pipeline. That's partly, it's the architecture of our platform. You know, basically the platform, the pipeline is the deployment object. So any interaction with deployments goes through the pipeline. The model explainability, yes, it is available from other ecosystems. What we are specifically trying to do is we are trying to sort of tighten the link between these analyses and the actual data that's coming in production. I mean, you can and you should do things like SHAP analysis prior to deployment on, you know, your training data or any other sample data that you have. That's a really good idea. Just to make sure that you're not deploying something that has unintended side effects. You know, we are trying to provide a way for people to interact with the models that will, while they're in production, with the real life data that's coming through in production, being able to do explainability specifically on those predictions, those instances, in an efficient way that is accessible to data scientists and other business partners, you know, without having to know the interior workings of the platform. Source code, if you look in our docs, we have a lot of tutorials that will give you, and I see Dipika just added the docs link to the chat, so please do check that out. And the recording session, I'll defer that to Bill. Data privacy. Okay, so we didn't touch on this too much. I think what we did not emphasize here is this is not software as a service. This platform is on, essentially, it's in your infrastructure. I'm not going to say on-prem because it's going to be in your cloud infrastructure if you have a cloud infrastructure. We do not see, Wallaroo do not see any of your data, only you do. So the platform is intended to integrate with whatever infrastructure you already have.
Yeah. So Wallaroo platform is like completely platform agnostic, and it's your data, your model, your infrastructure, where you're running. Everything is yours.
Again, I'm going to defer that one to Dipika. She probably knows where that sort of information is. Comparison of Wallaroo with other platforms. Yeah.
Yes, we do. We actually have a performance benchmarking number also on our website. Let me share the numbers with you.
Great. So thanks very much to everybody for attending. We hope that you got some value out of this. And we hope that a lot of you go on to check out our platform, check out our community edition, and find out for yourself how useful it can be for you. Thank you.
Thank you all.
Great, thanks. Yeah, by the way, you can send those links to me, and later I can share to all of attendees. You know, the benchmark you mentioned about.
Yeah, I'll send it to you, Cam. Yeah.
Okay, yeah, and other resources links I can send it to our attendees. For the recordings, again, the recording is recorded. You will get email notification once the recording is ready to watch on YouTube. With that, it concludes today's event. Again, thanks Nina and Dipika for the presentation and talk to our communities. And I hope everyone have learning something. By the way, we have a last minute, last questions coming up. Maybe you want to take a quick look.
Yeah. There's
Go ahead,
one more
Dipika.
question.
In terms of support for model formats, is the support the same as Onyx? You want to take that, Dipika?
Yeah. So we actually, just for the sake of example, we use the Onyx, but it's really, as I mentioned, you can bring your own model in any format, whether it's TensorFlow or PyTorch or sklearn, any model. Yeah, we'll take care of the conversion, and internally we convert to our own model object.
Thanks.
Yeah. I would just like to say thank you very much, everybody, for listening to us. We are very early in the journey and would like your feedback. If you guys really go and check out the community edition, play with it, and let us know your feedback, how it's helping the community actually, so that we can go and build out an awesome product, which was focusing on the data scientists.
Right.